Let's go.
Okay, so I found this paper and it seemed pretty cool, so I wanted to present it to our group. So this one, it's kind of a mouthful, but it was a really cool paper. So it's called Sparse Multi-Channel Variational Autoencoder for the Joint Analysis of Heterogeneous Data. So with heterogeneous data, I think we all like have a relevance for this, but so it's basically just data that comes from different sources, and so I think people interpret this in a lot of different ways. But for us, from what I understand, it just kind of means like data from different measurement devices like EEG, fMRI, stuff like that. But I guess you could interpret this in a lot of different ways, like measurements from different like scales or distributions and different kind of like levels of measurement. But it's basically data that's not like homogeneous, not all together, but something complementary about the different data. So that's what's kind of useful for us. And yeah, so obviously the data that we collect represents some kind of an underlying system. So it's cool to collect this kind of heterogeneous data because maybe it's complementary in nature. That's something that we should consider. So when it comes to Alzheimer's disease, obviously there's like a complex pathology that goes into that, as we learned from what Armina presented a while ago. So there's a lot of different things that maybe could trigger Alzheimer's disease or progression. And so that could come down to like genetic factors, lifestyle factors. And I think it's still kind of an open question in research, exactly how those processes are intertwined and how they all contribute in different ways. But we also take a lot of different kinds of measurements of people with Alzheimer's disease. So each one of these different like biological factors could show up in different ways in these modalities in which we collect data. So we can collect data in a lot of different ways or modalities. So we have like textual data, we can have like biospecimen data, image data, genetic data. So I guess all the different underlying factors can manifest themselves in different ways and degrees in this these different modes of data. So that's why I think it's kind of people are looking at this information overlap in all these different modalities. And I guess that's still a bit of an open question of like how to quantify that or exactly what is the like process for how these different data types interact and stuff. So and again, like there's the underlying causes, but then there's also like the ways that it manifests itself biologically that we see, which is like atrophy in the brain, connectivity changes in the plaques and stuff like that. So I guess that's what we're trying to understand with the information overlap. But as we know, we all work with the neuroimage data, which obviously has, it's in a high dimensional space. So it makes it pretty hard, I guess, to just work with it outright and with like traditional methods. Because I mean, just thinking about it, like the neuroimage data itself has over 1 million voxels, and so that means like each subject is represented with like a 1 million dimensional vector. And so I guess it makes the feature space really sparse. So it can just overall just make the problem really hard if you just think about it from the original like degree of representation. So that's why we do dimensionality reduction. So basically the extreme nature of neuroimaging data pushes for some kind of a form of reducing the data to a way that we can understand it. So all of us work with stuff like this. So we have like the NeuroMark template here. This is the V1 template with the 53 components, which is just a form of dimensionality reduction on the neuroimage data to like 53 common brain networks. It just makes it easier to work with. Yeah, there's yeah. And yeah, so basically we just need to do dimensionality reduction because it enables like traditional methods, but also just allows us to kind of like find patterns in the data and visualize the data. So I wanted to just kind of include this slide because here's an example of like some maybe like this model was trained on some face data, and to find some kind of like a latent representation of the face, and you can just kind of maybe sample from of facial representations, and like you can have these different sliders to toggle the values of the latent representation of the face. And so ideally it would be pretty cool if we had something like this for our brain, where we can just kind of toggle these different factors, and each of these factors have like a potential biological representation, like age or something like this, or maybe some kind of like this like biological things that are happening that cause disease progression. But yeah, I guess there's other reasons too for this whole dimensionality reduction stuff. So in the paper, they talk about traditional methods for trying to find a latent representation or find these latent factors to represent the brain data. So some of these that they talk about in the beginning are recognition methods, which are basically just projecting the observations to a lower dimensional space. So there's like some traditional methods for doing that. And so what these do is they project the observations to a lower dimensional space and enforce these desired characteristics of the data. Like, for example, the CCA enforces like maximum correlation between these latent components. And they just kind of mention, obviously, that these are not generative. You can't really sample from the latent space with these recognition methods. And I guess they don't really know how to handle missing data. And then, so they talk about some of the work that's being done with generative methods. So essentially what these methods do is they try to learn like values that parameterize a probability distribution. And once you have that, you can just take random samples from that probability distribution. And so that's what they call generative. So this is another example that they wanted to point out, which is this Bayesian correlation analysis. They're claiming it doesn't really scale well, and it's typically just done with like a single channel. And then they talk about traditional VAEs, you know, like they don't have an interpretable latent space or something like that. That's like one of their critiques of the paper of the VAE model.
Interpretable.
See, I'm trying to remember what they said exactly.
It's normal others.
So it says modeling. Oh, okay. So they're saying, like, if you want to do some kind of a multimodal analysis with a VAE, you would need to like concatenate those representations at the latent space. But they're saying that this it's difficult to disentangle the contribution of each different modality if you do this concatenation thing. So I guess that's kind of what they're trying to say here. So basically an autoencoder is just two neural networks that try to reconstruct an image. So how that works is they take in the input here, which is a high, you know, the original dimensional space of the input data. And then through a feed-forward network, they just map it down to this low dimensional space. And so this creates a bottleneck here. So it tries to compress the data down to a smaller space. And then the weights here learn to map it back to a larger dimensional space. And so how this is trained, you don't even need labels for this. You just use the reconstruction error from the input to the output. So traditionally, people use what's called an undercomplete autoencoder, which is where, like I just described, there's like this bottleneck in the middle where they try to learn some kind of a code for the input data. So obviously having this smaller dimensional space, there's information loss, but this forces some kind of a dimensionality reduction. And so like with linear methods like PCA, this is, it also does a dimensionality reduction, but this is like a nonlinear dimensionality reduction. So it's better than PCA in that way. And this facilitates this latent dimensional representation. Now, you might not know what the dimensions in this latent space represent, especially for something like brain data. But that's what happens with these guys, the undercomplete autoencoder. And but what people don't really, maybe I haven't heard people talking about is this concept of an overcomplete autoencoder, basically because this doesn't really make sense on its own. Because what we do is we take the input data and we actually have a larger hidden dimensional space. So you're kind of thinking, okay, why would you do this? Because all the model has to do is just copy the input, to the hidden space and then copy it again from the output space. But why people sometimes do stuff like this is for like sparse autoencoders and things like that. Because what you can actually do here is learn like a more detailed representation. And what you can do is, potentially learn things that are not particularly like all the way relevant to your task, but you can kind of prune those out and maybe learn those like disentangled representations. But typically what people do with this, if they ever have an overcomplete autoencoder, is they'll do this thing where they prune here in the hidden layer. And so what they want to do here is they try to set as many activations to zeros as possible. And what this does is the model essentially, through whatever kind of like criterion you use for pruning, the model determines which latent dimensions are the most important to the input. Yeah, so what's cool about this is it can kind of learn these meaningful part space representations, which we'll get into later. But basically kind of just a small background on what this paper does. Because they use a variational autoencoder, which is a probabilistic model. So when we work with the data X, this is some observed data that we have, which is, for us, images and other kinds of measurements. And for us, that's neuroimage data. And we assume that there's some kind of latent or unseen factors that are like underlying this data. So for an image, this might be like the position in which you're capturing the photo. But for neuroimage data, it could be, age or other biological processes. We don't necessarily know. So our goal is to basically try to figure out what is the distribution of this latent space or these latent variables. And the way to do that is to start by writing this conditional probability here, which is the probability of observing some latent variable given our observation of X, which is the neuroimage data. So to start thinking about this, you can just write it using Bayes' rule, like in this way. But the issue that comes up in this whole problem is that this denominator is considered intractable. Because to basically evaluate this, you have to integrate over all the possible values of z, which is the latent variable. And when it's in a high dimensional space, it's just basically computationally impossible to compute. So then what people do from here is, and I won't just go through the whole math, but they can just kind of like manipulate this. Okay, so let me go back. So this probability here is what we're trying to model. So we just estimated, we estimate this using some kind of a common distribution that we know about, like the normal distribution or the Gaussian distribution. And then so what people get to is this thing, which is called the evidence lower bound. And so it's basically, you can write this expression here, which is an assessment of how well our family distribution or parameterized distribution models this latent distribution. And people can get it to this form, which is where We have here, which is the evidence lower bound, and we have this thing, which is the evidence. And here, this kind of brings us to what a variational autoencoder is. So what we have is the encoder, which is sometimes called the inference network. And so this network just learns to map the input to whatever parameters of your distribution. So for example, if you're using like a Gaussian distribution, this network will take the input and just map it to like whatever parameters characterize the distribution of like a Gaussian. So we know that's like a mu vector and like a matrix for the covariance. And from there, what we do is once the network has these values for the distribution, you just sample some vector from that distribution. It's like a multivariate Gaussian. And so that actually gives you a sample that comes from that distribution. And this distribution represents X, given that we've observed, this distribution represents or characterizes the latent variable, given that we observe some image, like neuroimage data. So then, yeah, what we do is after we sample it, then we have the decoder network that takes this sample data, this sample latent representation, and tries to reconstruct the actual input data from this latent representation that we sampled from a distribution here. And so this is just trained using that loss function that I showed in the previous slide, which is the elbow loss. And so that essentially operates off of just the reconstruction loss and the KL divergence between the actual distribution and the estimated one. So then one more thing to remember about these models is that people have to do this thing which is called a reparameterization trick, because at this step where we have to like sample this vector z from the actual distribution that we're learning these parameters from, that makes this, it introduces this like random node into the computational graph. So it makes it to where the like back propagation doesn't work. So basically what they do here is they just take a random point epsilon from a normal distribution, and then they shift it by this sigma or by the covariance matrix, and so they scale it by the variance, and then they shift it by this mu. So that basically makes it like you're actually just taking a point from the distribution, but in doing this, it makes the back propagation possible. Okay. So, does anybody have any questions? I feel like I'm going kind of fast. Yeah, so this is what, getting into the paper now. So, what they do here is they have a multi-input, multi-output variational autoencoder, which can basically just reconstruct any data type from another data type. So what I mean by that is like every subject has all different kind of modalities, whether it's like PET or SMRI or maybe some kind of clinical information. So what their model does is it can take any modality and then just reconstruct the missing modality for a subject, and it can do some other cool stuff. And from here as well, it finds the shared interpretable latent factors that explain all of the data. So they found this healthy aging factor and this disease factor. So we'll talk a little bit more about what that means. But first, this is this is how their model is kind of constructed. So kind of like how they're deriving it, stuff like that. So the input, let's just say we have an input data X, and so this input data can come from any of the C channels. So capital C is like all the different modalities that we have, and we can pick any modality that we want, which is just represented by this lowercase c. And so they're just talking about this X right now as this d-dimensional vector. And then we have Z, which is sampled from this probability distribution, and Z is our latent variable. And P is our decoder, which is modeling the likelihood of observing data point X given some latent representation Z that we don't really know. So each modality C has its own likelihood distribution from some family of like known probability distributions. And they're parameterized by this theta. So theta is like the set of weights or parameters that define a probability distribution. And there are C of these different probability distributions, one for each channel, and each one has its own parameters. And it's the same thing as well for these generative parameters as well. And so there's the encoder. And so this one, we have the latent variable, which this is an L dimensional variable. We don't necessarily know like how big this vector is. So that's, I guess, one of the problems with a variational autoencoder and other encoder models is that they're not sure like what is the dimension of the latent space, especially for like brain data. We maybe just don't know. And then this X of C, this is just some input data for a given subject of a particular modality.
The key there, right? Sorry to interrupt. The key there is that Z is shared between modalities, right?
Okay, we'll learn about this more in like maybe 2 slides, but actually there are C encoders and C decoders, and there's also C latent spaces. So each channel has its own latent space.
Okay.
But they're all updated together.
Why don't they index Z?
What?
Why don't they index Z?
Yeah, that's a bit confusing. I'm not sure.
Anyway.
Yeah. But so this is their loss function. So this is essentially how it works. Yeah, maybe I should have talked about that a bit more. But like I said, there's an encoder for each channel, and there's a decoder for each channel. And each channel, which is a modality, has its own latent space. Now, how their loss function works is what they do is they have the typical like KL divergence term from a regular Bay, which is where they're measuring like how well they are reconstructing, like how well are they representing this distribution here. But they have this thing here, which is measuring the reconstruction loss. Okay, so you basically, it doesn't really make sense for me. I was like, oh, why are they having all like multiple latent spaces, but then they're saying that there's a shared latent space. So that's where the loss function comes in. So let's take a look at this term LC, which is the expected log likelihood of decoding each channel from the latent representation of channel C only. So this is an example of how it works. So let's say we have an input of a subject's SMRI file. So in that way, we're picking one of these values of C. And from here, the encoder encodes this input data point X to its latent representation. Now, when they're training this loss function, what they're trying to do is for that encoding for SMRI, they will pass this through every decoder for each other channel, and they'll measure the loss of reconstructing different modalities from the latent representation of, say, SMRI. So then they'll just accumulate all those different losses in this function here, and that'll just go into their overall loss function. So basically, for each input data point, let's say SMRI, they try to construct all the different modality types for that subject. And then they update the model parameters based on the loss of reconstructing that data point to the other modalities. So here in this equation, when the C here is equal to the same channel from which this data point came from, this is just its own self-reconstruction term. But then when the C is not equal to the actual channel number from which this modality came from, it's the cross-reconstruction loss. So how is this different from the regular VAE? This latent space, it's not concatenated. So since they have like these disjoint latent spaces, they're actually learning jointly rather than just having a concatenated vector. And oh yeah.
What do they mean by that? Because I'm not clear based on your description so far. It's what I've heard is separate encoders, separate latent spaces, separate decoders, separate loss functions.
No, there's only one loss function.
One loss function.
Yeah.
Okay, so they're just accumulating in loss. Is that all? So
yeah.
That's what they mean by jointly?
Yeah, so there's separate encoders and decoders and latent spaces, but their loss function for each data point looks at the loss for reconstructing one modality, reconstructing all the modalities for one modality's given latent representation. It's really hard because they don't have an actual diagram of their setup.
Yeah, it doesn't check out. I agree. Just so if you have n encoders and n decoders, there you have n sub z's. But if you go back one slide, you only have one z from which you reconstruct all the modalities, which means there's only one latent space into which every modality.
That's why I thought based on the
encodes, and then yeah, exactly based on the notation. So how is the separated? I don't see how they're modality specific latent space.
You were saying, Joanne, about them inferring or doing the reconstruction from other modalities latent spaces. So that do they take the latents or they take the parameters maybe from each distribution and use them to resample? I don't like that. Yeah, there's a detail there. Pretty important that I missed.
Multiple encoders all create the same Z. Multiple decoders all make the same Z.
Yeah, that would make sense.
Yeah.
A lot of.
But Z then is overlaid. Everything is in the same space. But this is what you usually want.
That's what I thought they were talking about interpretability as well, because you could look at like the transitions between different modalities.
The modality gaps.
Yeah, exactly. Yeah, exactly.
Okay, maybe that is what they're doing, because I was confused too. Like, why is there not a C here? So maybe there is one latent space.
Like they
Correctly, it's like there is one single latent space and there are C encoders, which potentially make different things in this latent space. So what they're trying to do is they're trying to make the encoders to produce the same kind of distribution as latent space.
Yeah, but they're all branching and they converge on that latent space. That's what we were.
Because when you're updating the parameters, the same parameters mu and sigma are updated regardless of which input modality was there.
There'll probably be mu and sigma from different encoders, right? And then they. All right, no, yeah, I don't know.
The latent space. Latent space is a Gaussian.
Yeah, I was trying to think but it ends up just being other ways of concatenating.
Latent space is what is it called? Diagonal covariance Gaussian. That's how autoencoder works. There is no cross covariances there.
Yeah. Okay. Yeah, because I got a bit confused. I think because it says
Well, it would be easy to do colored noise. I mean, yeah, just square root of covariance multiplication. Same idea.
Yeah, so it says LC is the expected log likelihood of decoding each channel from the latent representation of the channel XC only. So.
Well, I mean, I guess it's a shorthand for latent representation created or mapped by channel XC, but it's in the same latent space. Latent representation is different, but the latent space is the same. That's why there is no sub C and Z.
Oh yeah. Okay.
And that's the only kind of logical things for catching the
Yeah. Okay, that's an important point. Okay.
Just gotta ask questions, so I'm confused.
Okay. Yeah. So if we had this stacked VAE situation, we would have all of these disjoint latent spaces. So maybe that's that's what they're saying that we're not doing. Okay. So this is what they're actually they're modeling the latent Z distribution as a Gaussian. And so there's kind of a lot going on here, but they have these two matrices for each distribution. So for the generative, for the decoder, they have this generative matrix, which represents these decoder weights, and it's a linear map that transforms Z to X. And then they have this vector G that has these variances of each channel, which is not explained by Z. And here, so from what I'm aware, we use these variational parameters, which are used by the encoder to map the input data X down to this mu and sigma value that characterize the latent distribution. So these are both matrices of weights that are learned by the encoder to just do this mapping of X to Z. Now, getting kind of back to that overcomplete autoencoder case, they have this question of how to actually choose the size of their latent space. So how they start is with this heuristic method, and what they do on like a synthetic data set is they vary the size of the input of the latent space. So they vary the size of the latent dimension, and then they kind of look at the loss for some kind of an inflection point as to like what would be a good choice for that. So they're just kind of using that as a heuristic. And then they also do this sparsity stuff where they use variational sparsity, where the network learns a good dropout for different weights. So they found, they found with this like automatic sparsity stuff, that if they just start with this over complete latent space and they just let the model prune the dimensions, that they were able to kind of achieve what they wanted to. So we'll talk about that a little bit more.
Talk more about variational dropout. I'm not familiar how that's
Oh,
different from normal dropout. Won't give you sparsity really, right? It's a regularizer, but it's like just because you have a probability of dropping neurons doesn't mean those neurons won't get populated in the next iteration, right? But I'm missing something else on how dropout versus sparsity.
So from what I understand, and this was kind of new to me as well, but so regular dropout is just some kind of like a hyperparameter that you set in your model, which just randomly drops a percent of like the activations throughout your network. But then for this variational sparsity, they actually treat each weight has like an uncertainty value that the model learns. So like different uncertainty values, maybe that lead to like a higher loss, the model learns to like adjust those values and drop them. Yeah. Yeah. So they use this variational dropout in their overcomplete kind of latent space. It's not overcomplete technically because it's not bigger than the input dimension, but it's kind of like bigger than they actually need. So they can kind of see what size they need to choose. So they use two different data sets for their experiments. So they made a synthetic data set so that they know the ground truth for their experiments, because with the neuroimage data, we have this like potential latent representation that we don't really know what the ground truth is. I mean, that's, I guess, kind of an open question. But here, they're just able to automatically generate this latent vector and see how well their model can recover this. So they kind of just generate this random data, and they kind of play with how many channels or modalities that they have with this data. And they also play with the channel dimension. And they also play with how big should we make the latent space and stuff like that. And then for the medical imaging data, after they've kind of done this synthetic data, they kind of learned how to train their model a little bit better and stuff like that, like what's good dropout values and stuff. And so after they do that, they do some experiments with the adenine data set, which is an Alzheimer's data set. And so they look at their model, like reconstruction and like prediction ability compared to some other like baseline models. And then another cool step that they do is they do some like generation, and they kind of look at like pathological aging and cross modality generation. So that's pretty cool. We'll get into that. So this is how they made their synthetic data set. So what they do here is, did they generate a random data point, assuming that there's this decoding matrix that some underlying decoding matrix, and there's also some underlying vector from which x is generated from, and so they just kind of generate all these different data points across different modalities. So each matrix here is a decoding matrix, and each modality has a different kind of a decoding matrix. And then for the ADNI data set, they just selected 504 subjects from there. And so they have a clinical channel, which is these characteristics. There's 6 characteristics that they chose. And then they have an imaging channel, which has these 3 different kinds of imaging data. So they have just regular SMRI, and they have this amyloid PET and this FDG PET. It's some kind of functional PET imaging. So to just pre-process this data, they use an AEL atlas, and they got the 90 regions. So each region has just one intensity value.
We just say PET. We just say PET.
Oh, that, okay.
No, it says PET.
This is how you know I don't really work with PET.
Yeah, exactly. So, welcome to the club. But, yeah, you have to pretend you know what you're talking about. PET.
Okay.
That's it.
Okay, so yeah, so we have these 2 PET modalities, and then we have SMRI, which is a structural. So what they do is they train their regular model, which is sparse model, and then they also train the non-sparse version of their model, and they also look at like a stack of VAEs, and they also just look at a regular VAE. So this is some of what they found with their synthetic data experiments. Here they're looking at basically how many activations got set to 0 for their sparse model. Like how well is their sparse model learning how to drop out certain activations. And they're looking at activations in the latent space as well as the generative parameters. So you can just kind of see that their sparse model is obviously has a lot more 0 activations. And here they're looking at the reconstruction loss for the different kind of baselines that they compare to. So I think generally they're saying that like their model has lower reconstruction loss. And so apparently the number of channels really has a lot to do. So apparently like more channels that you have, the model can better reconstruct the output. And here's what they were kind of looking at for how do we decide, in the beginning, what to choose for the dimension of the latent space. So what they did here is they just kind of played with that latent dimension for their synthetic data. And what this plot shows is like for the ground truth latent dimension. So they made like, for example, a latent dimension a latent space that was only 1 dimensional. And they wanted to see but then they actually made like the hidden layer of their model up to 20 dimensions, but the true ground truth was only 1 dimensional. So they wanted to see like which activations actually got dropped by their sparse model, and so they see like very frequently the true number of like dimensions got dropped. So these have like a really low dropout rate because for ground truth, this one is actually 10-dimensional latent representation. So these are like the most important dimensions of their latent space because their model was not dropping them a lot. But for the other like dimensions that were not really needed, the model set those activations to 0 quite frequently.
That's bad actually for their initial story. Their initial story of overcomplete representation was like we will create 1500 types of eyes and noses and cheeks and stuff like that. And to create a new person, we'll sample specific nose and stuff. And here they say, no, the dimensionality of entire space is actually not needed. We will create a dense dimensionality, which is just, it's not overcomplete. For overcomplete, you will have a uniform kind of sampling because you're taking like you need all of those features at some point for some samples. So I like this is counter to the claim that the model specifically says the actual dimensionality of the data is much smaller. Like that defies this dictionary learning over complete motivation or at least goal. I
Yeah.
don't know. What do you think, Brad? I don't know.
I think that sounds
Just like
that sounds right. Sorry, I was only half.
yeah. Just
Um,
okay. Anyways, yeah. Go on. It's just
Yeah, I know. I'm not really sure what the whole motivation of like having a whole lot of latent dimension is, but I think maybe this exercise they're trying to see like
I think they did motivate it correctly. They did motivate it correctly, but or clearly. But this doesn't regarding the motivation. It doesn't. It looks like it doesn't learn over complete presentation. It learns dense compression.
Yeah.
I guess it means that the mechanism itself works, like the model can detect automatically how many dimensions it needs. So
But how many dimensions it needs is fine, but the model only detects the specific 10. It puts it's like it instead of creating overcomplete features, all of the like parts based or stuff, it just compresses everything into a small thing which is dense and that's it. It always selects this.
it's not clear what the benefit would be over a dense but smaller latent space.
Yeah.
like if
No, it is less interpretable.
But also this is the synthetic data, so that could be part of the reason why.
Oh, maybe, but at the same time, it just says I will favor those 10 dimensions instead of I will create parts-based representation, such that dimension 11 is useful to 10% of my data. Dimension 12 is useful to some other 5% of my data. Here is like, oh, after 11, nothing is useful. And so kind of, yeah, just weird.
I think I also kind of missed what the point of this figure is. Like it's so do they generate the data with a true low rank in the linear rank sense? Is that what they do?
Well, they they know the dimension of the latent representation because they generated it. So they know the exact latent vector that it came from.
So they are using a separate VAE to generate data.
No, they're just like using matrix multiplication.
So that's okay. This is
That's fair.
another graph I'm gonna have then. That's linear rank, linear latent dimensions, right? The whole point of the VAE is that you're finding a nonlinear latent representation of lower size. I don't get the argument here. Of course, you can reconstruct the linear latency. You can do that with anyone with a normal autoencoder.
PC.
Yeah.
Well, but I see the point better now, but the point still contradicts their motivation. It's they're saying, oh, yeah, we can recover the dimensionality of the space, but
If it's linear, for sure.
overcomplete representation is not about recovering dimensionality of the space. It's about capturing all of the variations.
Yeah.
So just
Yeah, but there is like a really stark drop off, which is like, okay, these have absolutely like basically no information, but these have all of it. I don't know.
well, that's how they constructed their simulation. It's just
This is, I wish they had read my dissertation, because this is what, I mean, honestly, like, this is, they used a linear mixture, there, you can show that you can recover linear rank with, even with a nonlinear model. So the whole argument I've made 5 times at NeurIPS, and they're like, no, that's too simple, apparently not. Right?
no, this is ICML.
Right? But, yeah, it's just.
No, it's still interesting.
Well, if they had somehow nonlinear, like if they had some sense of nonlinear rank, then I would think this is more interesting. But I'm like, okay, you could do this with a normal autoencoder. Like this isn't. I don't get this figure in particular. I'm not entirely clear.
Mhm. So what, from what I'm understanding, they use this experiment to find this heuristic value of 0.2 for their like dropout criterion. Of course, they're using the variational dropout, but I think they're saying like 0.2 is like an important value for dropout for some reason. Which seems weird for them to extend that to like medical imaging data. I'm not sure if they do that exactly, but so what they do here is after they train their model on the ADNI data set, and this is their sparse model, which they trained on the ADNI data set. And again, this is the one that used the variational dropout, where the model learns the different uncertainty values for the weights in the network, and from those uncertainty values learns to drop certain like activations that are not important. Now, what they did here is they took the holdout data set, and after they trained the encoder, they mapped it down to the lower dimensional space. And then they plotted the top 2 most important dimensions. So that means plotted the 2 dimensions with the lowest dropout rate. And then once they did that, they colored the data points according to the age and diagnosis of the subject. And so what they found is basically like that the subjects are not, there's not like a random clustering, they're kind of clustering according to the different labels. So that's kind of, I guess, their way of showing, one way of showing that their model is like learning important representations. Now I think what would have been cool too, though, for this, maybe to have some kind of a comparison of like the different representations that were learned for like a regular VAE or the ones that were learned for like the stacked VAE and stuff like that. But this is only for their sparse model. And what they do here is after they train their model, they have these axes for like age and diagnosis according to how they plotted these points in the lower dimensional space, according to those two most important dimensions. So you can see like these are some of the values that they exist in. So what they do is they use the decoder to select a new data point. And they fix the axis along the diagnosis axis, and then they move throughout the aging axis to just see what is like the aging trajectory for a healthy subject, what is the aging trajectory for a dementia subject, and stuff like that. And so how they do that is like they pick a point in the latent space and they just vary one of the dimensions, and then they use that point, they push it through the decoder, and that generates a new data sample. And they just kind of look at that. And so what they're saying is that they found like some plausible aging per group. So they're seeing like different atrophy, maybe for the MRI and things like that for these specific PET modalities. And then, so this, the G matrix that we talked about earlier, which is this generative matrix, the rows of this matrix represent the observed features that we have. And then the columns of these features represent the latent features that the model learned. So they plotted the dimensions with the lowest dropout rate, which signify like the most important dimensions that their model learned. And so this is what they found after doing that. So you can see what they're saying is like their model learned, for example, like MRI, maybe there's like gray matter atrophy for like cognitive impairment and stuff like that. Like that's a useful feature for doing the prediction. Or with this, they learned these distinct features, which and I'm not really familiar with these two kind of modalities, but apparently they represent like different glucose uptake and deposits of the plaques and stuff like that.
In pets, they inject dye, like radioactive dye, is quickly removed from your system. I mean, it's not like radioactive, but yes, you need accelerators to prepare those. They kind of short-lived particles, and so you can detect them where they concentrate because they go where metabolic rates go, and you develop them in such a way that they bind or temporarily bind to what you are interested in. That's my 30 seconds understanding of going. And all I know is you say PET, not PT, and that's it.
Okay.
I can't talk much about it. But it's positron emission tomography. Yeah, that's what PET stands for. So that you have to inject a dye. So there is good and bad compared to fMRI and MRI with this. Or it's more structural in a sense. Its resolution is kind of blurry, but then it's more targeted. Unlike because you're injecting something you can control. So amyloid, okay, they're targeting amyloids.
Is anyone else getting caught up in the fact that it's so discrete? There's no.
Yeah, it's kind of weird because it's a Gaussian distribution, right? But maybe it's just mask heavily.
I think it's because they use the atlas, the AAL atlas. So there's 90 regions. Each region has one intensity value.
Oh, then
That makes sense.
Then it's just
Yeah.
But then one value. So they're plotting the mean or something.
It's still strange. This is uniform. They must have thresholded that down to see this better, because this must be like they probably have stuff above this threshold, but strange.
Yeah, they don't look for neuroimaging results in machine learning conferences.
Yeah, so kind of what I think they're going for here is you can see like worsening cognitive impairment represented in these low scores. And you can also see like gray matter atrophy in the SMRI channel, as well as like low glucose uptake in this channel here is what they're claiming in the temporal lobes, as well as these high amyloid deposits in this channel. So they're kind of just looking at the weights that were learned by their model and just kind of using that as like an interpretability aspect. But yes, that's it for my presentation today.
Great, thanks, John. Any other points of discussion? So Jen is sending the class. Okay, I'm stopping the recordings. Thanks for listening.